Okay, good morning, everyone. Today we will I'll look over two examples for series parallel analysis, and then two small techniques, voltage division and current division. And then the final 10 minutes, we'll introduce new analysis techniques, node voltage analysis and mesh current analysis. Okay. Before I begin, how many of you know how to use MATLAB? Can you teach a class? Can you teach me? No, I'm just kidding. MATLAB is a very powerful computational tool. It's a software especially used in the scientific area, especially for engineering. I've seen a lot of usage in mechanical engineering and electrical engineering. When I was at UCSB, I knew a student, we had a student in our group who actually did his entire PhD in MATLAB computational simulation, mechanical engineering. So there are students who actually do the entire graduate studies, doctoral dissertations based on MATLAB. Again, it's a very powerful computational tool. If you have never used it, I highly recommend that you start now. If you go online and you search for jobs in your own fields, chances are more than 50% of those jobs will have MATLAB as a skill. Either it would be a required skill or at least a preferred skill. So if you start now, by the time you graduate, you'll have enough expertise in that area that you'll be able to list it as a skill. Okay. When I first started as an engineering student, we didn't have that. We didn't have a software. We didn't have computers. It was a long time ago, 1992. And so I learned MATLAB much later. Okay, I'm like barely at a beginner's level. But the first thing I typed in, literally, the first thing I typed in there was 2 + 2. Okay, that's how I began. But again, it's not just a calculator. It can calculate things for you, but again, it's a much more powerful tool. So you begin, and as you go along, you learn new skills. Cal Poly has an institutional license for MATLAB. You can download from their website, not Cal Poly's website. You can download it from MATLAB's website, install the software, and then activate it using your Cal Poly ID. So again, it's at no extra cost or no extra charge. So I guess it would be an institutional license. I don't know if it'd be a student version or not. But again, as long as you're a student at Cal Poly, you can activate it using your Cal Poly ID. You can run it on your laptop, desktop, even on your smartphones and your tablets. Okay, I have it on my smartphone. I have it on my laptop. Anytime I have a few moments I want to learn, I go ahead and use it for 5 minutes, 10 minutes at a time. So again, if you have never used it, go ahead and download it, install it, and you can perform simple calculations on it. And then, as you build up your skills, you can solve, higher level problems using that tool. Okay, so let's get into our topic for analysis for today, and that would be series parallel equivalent analysis. Where did I leave my pen? Oh, there it is. 3 examples, A, B, C. Let's look at A first. Series parallel analysis, the first step is always to find REQ as seen from the perspective of the source. So we remove the source from our analysis, and we find REQ between the terminals where the source was connected, right? We find REQ. So in this case, what do we see? We start at the farthest end, and we move towards the measurement terminal. In this case, we start at the rightmost end, and you move forward towards the front end. What do we see? R4 is connected. R4 has 2 terminals. Those 2 terminals are connected to R3, and they're connected to R2. So they are in parallel. So the next step after this, R3 and R4. And calculators out, and you tell me what the answer is for R5. What do we have? So R5 is R2 parallel R3 in parallel with R4, 20, 30, and 40. Any answers? He has 9.23. Anyone? Anyone have 8? 7? 9.23 once, twice, on 9.23. That is correct. So my REQ would be 19.23 ohms. R5 is 9.23. And 9.23, again, as a reminder for the concept, is smaller than the smallest value in that parallel network, right? 9.23 is smaller than 20. So now that we have REQ, we plug it back into the circuit with the voltage source. And then once you reduce, the purpose is that we apply Ohm's law to find out or determine the current or the voltage, as the case may be. So if we look at the voltage source Vs, which direction is the current flowing? How many of you say up? How many of you say down? No one? All right, let's go with the majority. It is going up, right? Current always goes minus to plus for a supply because it is supplying. Otherwise, our equations would never balance out. Makes a right turn. I'm going to call this as IS. Flows through R1, it reaches the junction, gets divided into 3 separate parts. So if it enters R1 through the left, what is the voltage polarity on the left of R1? Voltage polarity, plus or minus? How many of you say plus? How many of you say minus? Anyone for minus? No? All right. Plus and minus, which means my IS causes a voltage drop across REQ coming from the top. And I expand the circuit back up one step. That gives me R1 and R5. So R1, R5, current IS flowing in this direction, using plus minus, plus minus. So we compressed the circuit or reduced the circuit, not compressed. We reduced the circuit mathematically down to one single resistance. And then we are now expanding it up again. So once you reduce it down to REQ, you apply Ohm's law, you find the third quantity. In this case, the third quantity is the current IS, because we have V, we have R. We find I. That I is flowing through the entire circuit. So we expand it one step again, find VR1 or V1, then find V5. V5 is simply IS times R5. And then V5 is across the parallel combination of R2, R3, and R4. Okay, it's a parallel combination. So it's 2 nodes, 2 nodes, 2 nodes. So if you find V5 for R2, it's the same for all 3 of them. Make sense? Take 10 seconds, think over it. Let me know if you have any questions. Make sense? All good? Once you have V5, you can find I2 as V5 over R2. I3 is V5 over R3. And I4 is V5 over R4. We just apply Ohm's law again. Again, this is a simple application or continuous application of Ohm's law for every step. Okay, that's how you would solve a circuit using series parallel analysis. You take Ohm's law and you just apply it repeatedly over and over again. So first we apply it to find the current, then we apply it to find the voltage, then we apply it again to find the current. It's a repeated application. Any questions? Any questions at all? I'll wait until everyone finishes writing, and then let me know if you have any questions. No questions? Okay. All right. Just testing a little bit. So then let's look at B. You can solve this using electric circuit analysis, or you can solve it using logic. If you solve this, if you show this problem to a layperson, how would you think you can solve this using logic? You have a current source of 2 amps going down this pathway. And then it splits into 2 branches. Look at those branches. You have R1 and R2 in the first branch. Are they in parallel or are they in series? What's the value? Second branch, current splits into 2 branches. Both branches are an equal split. What's the value of I1 and I2? That's it. But let's look at the step-by-step analysis using our technique. This time I won't remove the source. I'm going to keep the source as it is, but we are trying to find Req as the perspective of the source, or from the perspective of the source. So I would combine the 2 resistances into one. I will call this as, let's say, call it R5, call this as R6. I1 comes down here, I2 comes down here. And then you combine R5 and R6 again into one single resistor, Req. And so you have current source IS, one single Req. What is the value of Req without any calculation? It says 10. How many of you agree? Agree? N number of resistors connected in parallel, all with the same value R. The Req is R over N. You can also apply the equation 20 times 20 divided by 20 plus 20 gives you 10. So Req in this case is 10 ohms. Voltage Vs, voltage Vs is the same for all 3 branches. So Vs would be equal to Is times Req, 2 times 10, 20 volts. 20 volts appears across the current source, appears across the first branch, also appears across the second branch of the resistance. You now have the voltage. You apply Ohm's law one more time, find I1 and find I2. Easy enough? Any questions? So the equations required would be I1 is Vs over R5 and I2 is Vs over R6. 20 divided by 20 gives you 1 amp in both branches. Does everyone see that? Right. All right. Any questions? Questions at all? Okay. Let's look at C. What do we see? You have a voltage source, 4 resistors in the circuit. Far right is R4. R4 is in series with R3. So the combination of R3 and R4 is equal to 40. 40 is in series with R2. I see some nods, then I see some shakes. Just trying to see if anyone is paying attention. Parallel or series? Parallel, right? 40 in parallel with 40 gives us 20 plus 30. And hey, look, Vs is of 30 volts. 30 divided by 30 gives us 1 amp. Let's look at the equations for C. So the circuit for C would look something like this. We have a voltage source. And again, our EQ from the perspective of the source. The source is not part of the analysis, right? I'm drawing it here. This would be R5. R5 is R3 plus R4. This is R2. This is R1. Let's see, do I have it right? R1, R2, R3, R4, yes. This is equal to, actually, R5 is equal to 40 ohms. So 40 and 40 in parallel gives me 20. This is the exact same circuit after reduction as circuit A. Right? You have IS coming from the voltage source. This is a voltage drop with the polarity as shown in the figure. This is R1. This is let's call it R6. R6 is the parallel combination of R2 and R5, which is 40 and 40 in parallel. It gives me 20. And then my total REQ is equal to 10 plus 20, 30 ohms, thereby giving me a IS value of 1 amp. Okay. Make sense? You reduce the circuit down to one single resistance, REQ, apply Ohm's law. If it's a voltage source, you apply Ohm's law and you find the current. If it's a current source, as we see in example B, you apply Ohm's law and you find the voltage. Once you have the voltage, once you have the current, then you expand the circuit up again step by step, apply Ohm's law at every single step, and you find the unknown quantities. Again, remember, Ohm's law has 3 quantities. V equals IR. If you have 2 of the quantities, you can solve the third. Right? Easy enough. So the homework based on this topic is due tonight. I think about 25% of the class has already submitted the entire homework. If you get stuck, if you need any help, you reach out to me. I have office hours in the afternoon. I'm also teaching from 3 to 6 in the lab in room number 126. So if you have any questions, you can stop by the lab. I'd be happy to answer those. Okay. Any questions right now? Okay. So let's look at 2 topics. Now this is This is not something that's covered in the physics class, okay? I don't like to call this a topic. It's not a topic. Voltage division and current division. Okay, this is voltage division. A couple of slides later, we have current division. Okay. These are not analysis techniques per se. These are shortcuts. Okay, these are shortcuts that allow us to calculate the voltage across a resistor or a current through a resistor. And these shortcuts are derived from Ohm's law. Okay, they are derived from Ohm's law. What kind of circuit is this? Series or parallel? What happens to current in a series circuit? Remains the same, because the current that appears in a series circuit is a combined effort of all the resistors that are working together. Okay, so the current that flows through a series circuit, it's quite evident because there is only one path for the current to flow through, right? It's quite evident. There's no other path for the current to flow through. So current is the same for all of them. What happens to voltage? It's right there in the word. It gets divided. So I is the same in a series circuit, whereas voltage gets divided. There's a short derivation. I will show the derivation, but that is not something that I will ask you. You have to remember, all of these are tools in your toolbox. You as an engineer decide which tools you wish to use to solve a circuit. Okay, so voltage division, current division, both are derived from Ohm's law. These are both shortcuts. It's not an analysis technique per se. It's just a shortcut that is derived from Ohm's law. So I will show you the derivation, but it's more important for you to understand what the technique is and how to use or apply the technique. What is the value of I in terms of Ohm's law? You have voltage VT that is applied. From Ohm's law, I is equal to V over R. So what is R in this case? I heard some murmurings. Req, right? Total equivalent resistance in that series circuit. Req for a series circuit is R1 plus R2 plus R3, right? So I, total current I that is flowing through R1, R2, and R3 is VT over Req. We apply Ohm's law again. What is V1? In terms of the current I, in terms of the resistance R1. Do you need to repeat the homework one again? Speaking up in class is never a penalty. Do not be hesitant to speak up in class for fear of being wrong, okay? If you speak up and your answer is incorrect, I will tell you, okay? I will tell you it's incorrect. But you will remember that moment because you spoke up in class and you realized the answer was incorrect. So you'll remember that concept far better than if you just keep mum and don't speak up. That's just true for all classes. Anytime you speak up, you might feel embarrassment. But again, the more you do, the more you speak up, the more you will learn. So again, that's just how I learned. And so hopefully I pass on that advice to other students also. Yes. So total current I that is flowing in the circuit would be the combined effort of R1, R2, and R3. And so the combined effort of all three in the series circuit would be R1 plus R2 plus R3, be Req. So when we apply Ohm's law would give me I is equal to V or R, but R in this case, as seen by the source, is R1 plus R2 plus R3, Req. So that was the question being asked. Why is it Req? And the answer is that's the total being seen by the source, as seen from the perspective of the source. So V1 is, oh, you're asking about this. Sorry. I misunderstood the question. It's not, it's an incomplete equation yet. It's not complete. So V1 is I times R1. We plug in the value of I, which is VT or REQ times R1. We rearrange the terms and we obtain V1, the voltage across R1, as a fraction of the total supply voltage VT, and the fraction is given by the ratio of the resistor to REQ. So V1 is a fraction of VT. The fraction is given by the ratio of R1 to REQ. That's voltage division in short. And so V2 is a fraction of V total. So V2 is a fraction of VT. The fraction is given by the ratio of R2 to REQ. And V3 is again a fraction of VT given by R3 over REQ. So it allows you to skip a step. You do not have to find the current if you don't wish to. Let's take a look at an example so it'll make more sense. We have a voltage source, V total of 15 volts, applied to a series connection of 4 resistances, REQ. What is REQ in this case? Tell me. Absolutely. 10 what? Kilo ohms. I missed the kilo in the 9 a.m. class. Luckily, a student pointed it out. So again, this would be, sorry, 10 raised to 3. So this would be 10 kilo ohms. The K is kind of important, right? Your answer would be completely incorrect. So REQ is 10 kilo ohms. If I wish to find V1 from voltage division principle, V1 is a fraction of V total. V total, VT times R1 or REQ. You don't even need a calculator for this. Therefore, V1 is 1.5 volts. 1.5 volts. V4 similarly is VT times R4 or REQ. 15 times. How much is this without using your calculators? 15 times 6 is 90 divided by 10, 9 volts. And of course, when you apply KVL, you will see it's 1.5 plus 1.5 plus 3 plus 9, which gives us 15 volts. Let's take a pause, write it down, think over it. Let me know if you have any questions. Yes. Oh, it indicates therefore. Good question. Sometimes some things that I'm used to, I don't think about. So mathematically, what we are conveying with this is we first write the equation, then we say, okay, my equation states REQ is this, then I plug in the values and it says, therefore, V1 is this one. How many of you are familiar with this symbol? Some of you. How about this one? Inverted. It's because of or since. Sometimes used in scientific notations. We know this because of. Or if I write an equation, I would write because of equation number 1 or equation number 2. Anytime, so thank you for pointing out. So anytime you see me doing something on the board, please speak up. Again, do not hesitate. It's a learning experience for everyone, okay? It's not just one student. Everybody can learn. All right, any other questions? Yes. Well, let's go to parallel. Question being asked is what happens if it's parallel? And I'll let you tell me what happens to voltage. It's constant. So for a parallel circuit, V remains the same, and then current gets divided. So for a series circuit, current remains the same. It's quite obvious because when you look at a circuit, current doesn't have any path. So when say obvious, I'm saying when we look at the image, it's obvious that current doesn't have any pathway to go through, so it remains the same for all of them. Voltage is not quite obvious unless we actually, we have studied physics and we know that voltage in a parallel circuit remains the same. So when I say it's quite obvious, I mean when we look at an image, it's obvious. But now that we know, it should be obvious that voltage in a parallel circuit remains the same. However, current gets divided. So as an example here, we use the current I total. It's 2 branches, only 2 resistors in a circuit, but you can have infinite connections. You can have infinite connections in parallel or infinite resistances in parallel. Current gets divided. Voltage remains the same. Excuse me. Voltage V here would be I total times Req, right? I total times Req, where Req is the parallel combination of R1 and R2. Or if you have 3 resistors, R1 parallel R2 parallel R3. 4 resistors, all 4 of them in parallel. We find Req as the parallel network of resistors. So I find the voltage as I total times Req, and each individual current is total voltage V divided by R1. You plug in the values for plug in the values for V, you get IT times Req over R1. So current division principle states that when you apply a current or you supply a current to a parallel network of resistors, a fraction of the total supply current flows through each resistor. The fraction is given by the ratio of Req to that resistor. So in this case, I1 would be equal to a fraction of I total. The fraction is given by Req to R1. The format of both equations remains exactly the same. The ratio of that fraction changes. Okay. In voltage division principle, Req is in the denominator. In current division, Req is in the numerator. These 2 topics are guaranteed on the final exam. If you have not yet taken a look at the final exam page has been up since the beginning of the quarter. It lists all the topics that will be assessed, and both of these topics are on there. So I2 in a similar manner would be equal to IT times Req or R2. Let's take a look at an example, and I'll let you tell me what Req is. Calculators out. And what is Req? Anyone? Someone said 6.66. How many of you have 6.66? Going once, going twice. Let's say it's 6.667 ohms. That is absolutely correct. I1 is IS times REQ over R1. IS is 15 amps. REQ is 6.667 divided by 10 ohms. What is the answer? I1 is, anyone? It's a nice round number. Absolutely. Without doing any calculations, what is R2? Current is inversely proportional to resistance. R2 is 3 times R1. So the current for R2 has to be 1/3 of I1. R3 is 6 times R1. So current I3 would be 1/6 of I1. Think on that, and then you can calculate and see if your answers match up. Write out the equation. You can calculate and see if it's 1/3 of I1 or not. Anyone? I2, anyone? Yes. 1/3 of 10, right? Okay, any questions? Any questions at all? So again, current division, voltage division, not an analysis technique per se. They are shortcuts. They're shortcuts derived from Ohm's law. I will not assess or ask you to show me the derivation. What I will always ask you is show me the application of any analysis technique that we learn in this class. Okay. You learn the tools. These are all tools in your toolbox. You show me that you can use the tool, you can apply these techniques. Yes. Yes. Correct. All right. There are no more questions. We'll go into, well, we move forward and go into brand new analysis techniques. We'll learn 3 analysis techniques in this chapter: node voltage analysis, mesh current analysis, and superposition principle. Superposition principle is not a new analysis technique. It simply consists of taking a large circuit with multiple sources, and we break it up into individual small parts. And each small part or each small piece of the circuit is analyzed using series parallel analysis technique. Okay, so superposition is basically taking a large circuit or large analysis and breaking it up into individual analysis, small pieces. But the 2 techniques that we learn next, node voltage and mesh current, you can solve any circuit using these techniques. So I use this slide to actually explain what node voltage analysis would mean. But before we learn about node voltage analysis, we need to understand what node voltages are and what mesh currents are. So today, in the last 10 minutes, we'll learn about node voltages. So let's back up or think back to chapter 1. Use 2 subscript notation to indicate voltages. Electrical voltage is nothing but the electric potential difference between any 2 points in a circuit, right? We use a 2 subscript notation. For example, if it's VAB, we say it is voltage at A measured with reference to B, right? VAB is voltage measured at A with my reference point at B. There's always a point of reference. There's always a baseline for measuring voltage, right? In node voltage analysis, we use node voltages, and node voltages are indicated using a single subscript notation. single subscript notation. So node voltages use a single subscript notation. So it would simply be VA, VB, VC, and VD. The reference node or the reference point is implied. It's absent. Okay, we simply say VA, VB, VC, VD. Reference node is simply implied. How many nodes do we see in the circuit? They're marked A, B, C, D. B, C, and D up top. The entire bottom connection is a node. It's one single node. It might seem as if it's 3 different nodes, but again, they are just wires. Anything connected by a wire is just one long node. Electrically speaking, it's one single point. So the entire bottom connection is a node. And this indicator here shows that it's ground. Now, going a little off topic here, ground is indicated by a triangle or 3 parallel lines in the shape of a triangle as shown here. Sometimes it's also indicated by a simple end. The acronym used is GND, ground. Okay. We'll stay away from ground. It's actually irrelevant to the discussion here. Okay. We don't really care what point is ground. But in this case, it just indicates that at is the reference point of measurement. Okay. For the purposes of the analysis, this symbol is simply indicating the reference point of measurement. So in this circuit, node A is our reference node. That is the reference point of measurement for all nodes in the circuit. And that is the reference point of measurement for all nodes in the circuit. So if I state VB, node voltage B is VB, I am indicating VBA. The A is the reference node for this circuit, for this analysis, and it is implied. So it's VBA. It's voltage at B measured with my reference at A. That's what it means. VB is VBA. VC is VCA. VD is VDA. So what is VA? Because it's the voltage at A measured with reference to A. So it's BAA, which is kind of redundant. But the important point is that it has a value of 0 volts. And from there, I would state this, that choose any node as your reference node for the purposes of this analysis. Okay, and I will explain that statement. So let's take a step back and think back to chapter 1. Right? One of the earlier slides asks the question, what is circuit analysis? Right? Circuit analysis is the mathematical computation to find unknown quantities in a circuit. The unknown quantities are voltages and currents. So node voltage analysis, mesh current analysis they are analysis techniques to determine the unknown voltages and the unknown currents in a circuit. Okay. Now, if you wish to solve this mathematically, we need a set of equations to solve. So what we do with these techniques, both node voltage and mesh current, is we generate equations. And we generate equations by applying KCL and applying KVL. That's why it was very important at the beginning to refresh students' learning about KCL and KVL, because you will apply KCL and KVL and these techniques to generate these equations. These equations have unknown variables. These unknown variables are the node voltages and the mesh currents, of course, when we get to mesh current analysis. Okay. Again, I will repeat. Circuit analysis is the process to determine unknown quantities, meaning unknown voltages and unknown currents in a circuit. These mathematical analysis requires mathematical equations. These equations are generated by applying KVL and KCL. And these equations will have unknown variables. The unknown variables are the node voltages and the mesh currents. For the purposes of analysis, it does not matter which node you choose as your reference. You have 4 nodes in the circuit, A, B, C, D. You can choose any node you want as your reference node. There are 40 of you in a class. 10 of you could choose A, 10 of you could choose B, 10 of you could choose C, and 10 of you could choose D. You can choose any node as your reference point. The values you obtain in the other 3 nodes will be different. But when you calculate the resistor voltages, they will all turn out to be exactly the same value. That's the point. The point of circuit analysis is to determine the resistor voltages and the resistor currents. Doesn't matter what you choose as your reference node, your answers will always be always be the same at the end of your analysis. In this case, A is my reference node. So VA is equal to 0 volts. What other component is connected at A? We have the power source. We have 2 resistors and a power source connected at A. Which node is at the other end of that power source or that voltage source VS? B. We have A and we have B, and we have VS connected between the 2. We established that A has a potential of 0 volts because that's my reference for that purposes for this analysis. So what is VB? I heard some murmurings. It's VS. And so VB in this case is VS. You have 4 nodes in a circuit. If you have a voltage source in a circuit, you choose one end of that source as your reference. It automatically gives you the value at one end, which is 0 volts. It also gives you the value at the other end of the node. Out of 4 unknown variables, you have eliminated 2. You're now up to the $32,000 question. You eliminated 2. You only have 2 unknown variables. How many equations do we need? We need 2 equations. That's it. You apply KCL twice, and you generate those 2 equations, and you solve, and you get the answers for the other 2 variables. Once you have the values for all 4 variables, you can calculate the difference in potential at any 2 points in the circuit. Does that make sense? And of course, it'll make more sense once we go through an example. Okay, but the point is, if you have a voltage source, you choose one end. To keep things simple, you choose the negative end of the voltage source or voltage source as your reference. And first, you eliminate 2 nodes from your analysis. Choose one end of the voltage source. More often than not, the negative end of the voltage source as your reference node. And thus, you will have the answers for half of it. So we'll end class here today. Pick up here again on Friday. Homework is due tonight. If you get stuck, reach out to me. I have office hours in the afternoon. Send me an email. Come see me in person. See me over Zoom. I'd be more than happy to answer your questions. And then I will see you all on Friday.